So the basic one is the average case and the worst case. So what are they related? The average case will be our framework, and the worst case is basically the mental model of the two-player game. So you can think of the following. So now we go to the two-player game. You want to minimize this. What the heck is this? This is this one, right? So you want to minimize this, and this is what you can control, right? And this is player 2. And player 2 is probability got cosmograph. Okay. So you are going to play the two-player game. So what's the two-player game? Again, let me go back to the two-player game. So you have do your action, player 2 do nature respond, you suffer loss, and nature gains. Now, because we don't care about player 2, we only care about ourselves, so I only have 3 lines, I don't need to write down this. So back to the probability game. So you have to minimize x, because you are doing x, so you update x at time t. You can do any gradient, whatever algorithm you want, but now let's say you do some update. Then player 2 is probability got cosmograph, and then cosmograph can give you this. So let's say cosmograph, because he is probability god, he can give you the worst sample here. And this worst sample is based on this idea. So because he is a god, he can always give you the worst one. Don't forget, this have infinitely many possible ways to give you a number, right? But because he is a probability god, so he can give you always the worst one. Now what you do what you do, probability god do. So this is probability god, this is what you do, and you suffer this. Then what is the goal? The goal, of course, is to make this loss as small as possible. So you want to minimize this. And we have T round, right? So we minimize round 1, round 2, round 3, round 4, round 5, up to round T. And this is what you want to do. You want to minimize the cumulative loss on all the T round. And what's the probability cost role? Make you suffer. So you want to maximize this loss as much as possible. Okay. Now, here are 2 important things. Suppose probability cost is a real god, then it can really give you always the worst case. But now suppose probability cost cosmograph is a human. Even though he is a very strong mathematician, he's not perfect. So he can make mistake. So sometimes this one is not really the worst example. It's possible at some iteration, cosmograph give you this value is actually helping you, right? We are just saying we imagine cosmograph always give us the worst. So this is the theoretical worst. Practically, it's possible at some time cosmograph is sleepy and didn't give you the worst case, so slightly not so worse, that means for you it's better. But in the modeling, in the mathematics, we always assume it's the worst. So that means in reality, sometimes it's not that bad, not that pessimistic. But mathematically, we always consider the pessimistic. And this is the reason why we consider this worst case. And this is also the reason why we consider this and this. Since this is worst case, this is the worst, right? So of course this is here, right? Because for example, I have t equals 3 round. Okay, so in the average case, I have this 1, this 2, and this 3. And then in the worst case, because it's a worst, so let's say it gives you worst is 9,000, then for the 3 round, because the worst is always give you the worst number, then this will be the worst number. And this 3 number in the average case, because of probability, it may not hit 9,000, right? It can be here is 3, it can be here is 5,000. So of course, this thing add up together is larger than average. So that's why we have this sign. Okay? So in a sense, when we talk about the worst case, we are talking about here how bad it can be theoretically, because this is a theoretical upper bound. In practice, we don't believe we are so bad luck that every day we are super bad luck that there's a probability cost against you. So this is giving us how worse you can be in the end. But practically, you should see on average behavior. So these 2 things are different philosophy. This means how bad it can be in the worst case. This means on average. So we are going to work on this, but aware of this. So you can think of this as a guarantee, because you cannot be worse than this one. But practically, you are doing this one. Okay, so this is the meaning. And now, what will be the basic algorithm? Well, here's the basic algorithm. I want to fight against probability cost on minimizing this. So what's my problem? My problem is minimize, okay, my small x inside my big X, okay, and then on average, right? Because practically we talk about on average, and I have randomness in the distribution D, and then what? I have a function called small h taking value of x, And then what? I have a randomness here, right? This is the problem we want to solve. Okay, so now what are we going to do? We have t round. So first, I have this whole thing. At t round, I have this, right? So first, I'm going to take gradient. So let me recap. This is the gradient, right? x1, x2, blah, 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 and a vector. So first, I'm going to have a gradient expression. Once I have a gradient expression, I multiply with a step size called eta, and then you move negative because it's gradient descent, and I go down. And basically, this means what? If your step size is very big, that means you are fighting against Kolmogorov very bravely. And if your step size is very small, basically means you are scared. So this is the meaning, and this is a point. But here's the thing: this point and this thing, there's nothing on this big X here because you need to stay inside a set. And if you remember, I said you have inside a set S, you map something to a line. What happens if you are outside? You always map to infinity. Now, what happens if I'm outside? Then I will map to infinity. But I want to make it small. If I map to infinity, didn't I lose the game? So you have to project back. So what's project back? You are going to say, I have my point, which is this thing. Find in this X, the Y, that the distance of my Y to this green is the smallest. So find the closest point. So in the sense is this. I have my set. This is my set, big X. Suppose my point is xt here. And then after Kolmogorov and I do gradient descent, I jump to here. I'm now here. This is my x tilde, t plus 1. Oh no, I'm outside this. If I follow the infinity, I will jump to infinity. No, I don't want that. I will lose the game. So I need to come back. So what come back? I need to come back, right? So I come back. What does it mean come back? Find the point. Here is the red. That this distance is minimized. What the heck is this thing? This is the distance between the y and the x, right? And if this is minimized, then I find a point that is shortest to this point. If I can somehow solve this, then I get my point and I get my new point. And this thing is called projection onto this space. Projection, you write a pi because pi is a p, pronunciation is pi, so they write pi. Or you can write proj. Some people write proj. Actually, I write proj. And you go back to x means what? Because you have a rule, you have to stay inside a big X, so you are in the game. If you don't project, you lose the game. So that's why you need to project. So the picture is like this, whole picture. I have a set X. You start from here. Kolmogorov give you some random noise, and then you do gradient descent according to this random noise. So in the end, let's say you jump to here. Okay, you are this. No, you cannot go outside the set, otherwise you lose the game. So you come back. So you go to here. Now, after you come back, it's the same as you update to here, right? Now, this is round 1. So this thing is round 1. Now, round 2, you are here. Kolmogorov give you a random noise. And then you do gradient descent. Let's say, due to some reason, you go to here. Okay, this is your X. Now, you are outside the set. No way. You will lose the game. You have to come back. So you come back. These two things is the same as you go to here. So this is here, this is round 2. So now round 3, you keep going. So in the end, what happened in this trajectory is like you go from here, and then to here, and then to here, and then to here, maybe, and then in the end you do here. Maybe, so in the end you like do a doing this. Okay, something like this. So this is the idea. And in the procedure, actually you keep bouncing out, bouncing out, bouncing down, up, bouncing out, bouncing up, bouncing up. And all this going up is the gradient, that which relate to the Kolmogorov noise, because Kolmogorov want you to lose, so he try to draw you away. And then you go back by projection by staying in the game. Something like this. And this process will make function value on average go down. So this is the algorithm. So that's the algorithm. You first compute a gradient, and importantly, this is one sample because you only have 1 point. And then you do this gradient, step size minus, you get a point, and you project it back, and you suffer the loss, and you record it. So this is the idea. First, you have gradient, find a step size, basically mean how aggressive you find against probability God. After the aggressive step, you project back to feasible set. That means the X, otherwise you lose the game, and you suffer that, and you record it. this 3 line can be combined into 1 line. So basically like this. So this is one sample. So this whole thing is online projected gradient descent. Okay, I don't spell the whole name. This is online projected gradient descent. So projected this gradient descent. This part is gradient descent. Okay. Online is online. Okay, it's like this. So that's the 3 thing. This thing have the name online. So the online projected gradient descent. So that's the thing. Okay, this is the basic algorithm. Now, because this thing is one sample, so therefore there are several important things. You can actually do the following. This is now Monte Carlo gradient descent. This is different. Is instead of this, this is this, right? Now here you change something. You saying I take many samples. So you have a lot of them, right? You can have a lot of them, right? And all of them, you sum all of them. So I put a sum here, and then you take the average. And let's say you take n of them. Then this is also a gradient, right? So in a sense, you are replacing this part by an average of this, right? Then these two are different. This is Monte Carlo gradient descent. This is one sample online gradient descent, which next week I will talk about what is their difference next week. So now I'm just telling you they are different. Okay. And what's the remaining time? The remaining time is I have not many time left. I don't want to overload your brain too much of the content. So the detail is we are assuming Kolmogorov select the worst random noise. You are doing is to hedge against the worst case. In practice, actually, it's not the case because it's probable that Kolmogorov is sleepy, make mistake. So therefore, we're talking about the worst case guarantee. Okay. And the second thing is, if I do everything like this, how do I measure? Is this good? We're talking about something called regret. Regret is something called sublinear regret. I'll talk about sublinear soon. And it means if I run many terms, eventually I beat Kolmogorov. That's the idea. Now, we're going to talk about projection. So, because in here, I have this thing. So, I need to talk about this thing. So, this is next week. I'm not going to talk about this right now. So, I'm going to talk about the optimization to learning. So, what we just discussed is we want to minimize the average behavior of an H under randomness C. We do one sample online projected gradient descent OPGD against the probability graph. This is about optimization, right? We can have this philosophy to learning. So this is the learning. What is learning? In learning, we no longer have minimize something. We just fit data, fit neural net, fit training, right? So the learning basically is we do some parameter tuning in a neural net or model update. Then offline and online now have different meaning. Offline basically means stationary, no change, no dynamic change, all data at once. But online means data coming step by step, sequentially. And since data come many times, you will rarely see data twice, and you have changing. And you can assume data is behavior is changing. So that's the difference between learning and optimization. Online optimization and online learning have slightly different focus.